here into the background now.
Thank you. So, yeah, so this is work with my colleagues well typed. This is part of the GHC Parallel Project. We've been working on parallel profiling tools to help our partner. We've got a number of companies that are trying to write real parallel programs, and we're helping them fix bugs and helping them learn Haskell. But one of the things we're doing is improving the profiling tools to help them parallelize their data. So, in particular, Nikolai has spent a lot of time hacking on this. So, a lot of the credit for what I will be showing you is down to Nikolai's excellent hacking. He's unfortunately not here. So the point of this talk is about profiling parallel Haskell programs, right? There's a few single-threaded use cases I'll briefly mention, but the main purpose is trying to understand why is my parallel program not running faster? You know, I parallelized it, you know, I sprinkled it with par and par list and whatever, and it's still just as slow as it was before. Why? It's slower. What is going on? Why? So that's the point of these profiling tools, to try and help you answer that sort of why question. So yes, the main point is this. I'll be looking particularly at the par Spark model. But I'll briefly, because my assumption is that most of you guys have seen ThreadScope, maybe heard of it, you sort of know it's a parallel profiling tool, but you've never actually used it, is my assumption. So I'll go over a little bit of what the basic stuff that ThreadScope does, and then I'll explain what extra things we've been adding. So where does this fit in the sort of context of the family of various GHC tracing profiling systems? So you've got time profiling and heap profiling. The HPC code coverage is sort of related, GHC debugger. But this thing that we'll be talking about is event tracing. So this is, indeed, it's currently, I'm not actually quite sure about HPC, but it's really the main one at the moment that works in parallel. The other ones don't work in the threaded, if you're not more than one core. So what does event tracing do? It has an event log, and in the runtime system, whenever certain things happen, it writes out little events into an event log. So things like, this Haskell thread just started running, this Haskell thread stopped running. We started doing a GC, we stopped doing a GC. You can also emit string messages into the event log from in Haskell. And there's various other events that happen in the RTS that get logged. And this system is reasonably efficient. It's got quite a low overhead per event. It's dumped into a binary log file, and Simon and the people who developed it first spent quite a lot of effort trying to make it really efficient, so it doesn't interfere too much with the runtime of the program. Whereas, for example, if any of you used the ordinary time and heap profiling in GHC, you'll know that it makes quite a significant difference to the runtime because it changes the way it's compiled. Whereas this is just changing what the RTS does. So there's this event log format, which is specified. It's a binary format. It's somewhat extensible. You can add new kinds of events. And this infrastructure actually is also used by other people now. Mercury, which is not even a Haskell compiler, Logic language, and Eden, which is a sort of distributed Haskell implementation. They all use this infrastructure now, which is quite nice. So we get a bit of reuse that way. So I'm just sort of here talking about what the shows you some graphical representation of what's going on. We'll go into more detail about what exactly it shows, but this is just first impressions. I said I'd mention that there are a few single-core uses, non-parallel uses. You can kind of get a visual impression of what the GC is doing. You can sort of see how frequently it's stopping and how long the interruptions are. You can get a fairly quick overview, which is sometimes useful. A technique that I think is a great idea, but we've not really done much yet, is running the same program twice with, say, different inputs or different parameters, and then comparing two runs in the same view. So if we use this GHC events merge thing, you can take two event logs, merge them into one. It makes it look to ThreadScope as if you've got a two-core machine, but actually they were two runs of the same program. So you could look at them like, you could compare, and this is actually a two-core program, but you could imagine looking at it that way and seeing what the differences were, a sort of a comparative debugging technique, which I have read. I've never used it myself, but I've read that this is a nice idea, so I thought, we can. Because we originally wanted this GHC merge for merging events from concurrent programs, distributed, but you can also use it in this comparative way. And there is more potential in the future for doing other single-threaded use cases.
Does merge always assume that the two events should have different cores? So if you say I actually have two ways to instrument the same program on the same core, and I just want to completely, like if I use Linux perf tools, generate one event log and GHC generate another.
Well, at the moment these would look like two cores from the point of view of ThreadScope. So integrating Linux perf events is sort of something we've been thinking about, and that would be a useful single-core use case where you can see, why is my program stopping? Is it blocking on I/O? What's it doing? But the main thing I want to concentrate on here is the parallel use case. So here's how you use it. You compile your program. You've got to specify threaded because you're going to be running on multiple cores. You specify event log to say link it with the event logging version of the RTS, and RTS logs, which is just annoying. Then you run your program and you specify -n however many cores you want to run it on, and then -l to say generate an event log. And the S is to say what kind of events you want to log. I'll come back to that. And then that will generate when the program runs, and when it terminates, there's an event log file that's written out. And then you look at that using ThreadScope. So that -ls, at the moment in GHC 7.2, there's only one class of events, which is scheduler events. And that actually includes scheduler events and GC events and everything else. In 7.4, I've broken it out so that we can specify them differently. But the default is, if you just say -l, you'll get the default set, which is usually what we want. I mention it because one of them is not in the default set, which is it's fully detailed Spark profiling. And that's what, these two are the new ones, and those are what I'm going to be concentrating on. So yeah, you can do more complicated things now. You can say, remove all of them and add back only the GC events. So this is the idea is we can have multiple classes of events and only emit the ones that you're actually interested in. So what do these things show you? This is the current sort of classic ThreadScope view. So at the top, you've got a graph showing the combined from all cores, the CPU usage of the mutator. So that is your code running, normal Haskell code, not running GC. Right? So GC time will, so you see here, well, I'll get ahead of myself. So you can see that, so the top, it will be using two cores. So we can see that this one is mostly using slightly less than one core. Except for a bit here where we have a little bit of parallel. So this is showing you a bad case. We're getting not very much parallel. And then this shows you for each core what's happening on each core. So green is code running, your mutator doing normal stuff, and the orange is GC running. So you can see here we've got a major GC. Both cores are stopped for a long period doing running GC, and that corresponds to the mutator time dropping to zero. And this maximum peak here corresponds to both cores at the same time doing a little bit of mutating. But generally, we can see that this is pretty bad. This is a bad example. You're getting a little bit of parallelism, but not zoom out, we have to sort of aggregate it somehow. So as you zoom in more, you get much more detail. And I'll do a demo later so you can see what it looks like as you zoom in and out and that sort of thing. So what sort of information can we see from this kind of view? Well, we can see, I don't mean just this one specifically, but sort of in general, the sorts of information that we can get from this view is, you can see quite clearly that you're not getting full, 4, 8, whatever core usage, because the graph is not hitting the top. You might see in some cases that one core is doing all the work. In this case, one core is doing all the work from here on, and even when it was 2 cores, it wasn't really very much going on. You can see cases where the work is badly distributed. So, for example, you might have working in parallel very well up until the very end, and that might tell you that your amount of work was in great big chunks and was unbalanced between the cores. And you couldn't make it better balanced because there were these massive chunks, and so there wasn't any. You can see if there's lots of sort of GC stutter. All these little white lines is minor GCs going on. So you can see if that's getting in the way of the performance. And the interruption effect of GCs, major GCs, minor GCs. But in general, you're just sort of seeing what is happening. You're not really seeing why. I mean, we still don't really have any hints. And I'm not showing you the program for this deliberately, but there's no indication of what we should be looking for, really, from this view, in my opinion. Sometimes just seeing this kind of thing can be enough of a hint. You go and look at your code and you scratch your head for a while and you somehow work out how that behavior corresponded to what the program is doing. But generally, I think it doesn't really sort of show you why they're different behavior. So it's still useful. You can try some experiments. You have an idea and you try it, and you see it. Suddenly the graph looks much better. So it can give you sort of feedback that way. But it's not really directing you to where the problem is. So slight characterization, but sort of at worst, it's just a sort of more detailed visual representation of the information you get from the RTS stats that you had, this many seconds of mutator and this many seconds of GC and this many. It's just telling you that, but in more detail. It's not really telling you anything about why. So you run it multiple times, you see that your overall time is decreased, but you don't know much more. So what we've been trying to do is to see why we're getting the effects we're getting. But for only the thesis is that to see why something's happening, you have to be more specific to the parallel model or paradigm you're using. You have to show information that's relevant to the model to the cost model, to the model of parallelism you're actually using. So we're looking at the Spark model. So this doesn't cover 4KO because that doesn't cover the primary net. I think you need to do something similar but different for each different model, basically. So yeah, we will be looking at the PAR one. So let me explain a little bit about how that works. So because to understand the graphs of what we're showing, we'll have to understand how the model works. So the PAR Spark model, each core has a task queue. Tasks are called sparks in this model, and the task queue is called Spark model. So these boxes are threads. So this one's idle, this core is idle, and this core has got 2 threads running. So one thread generates a spark, puts it into the spark queue. Another thread, because this core is idle, it starts a new thread to evaluate sparks and steals the spark from one side to the other, and that gives you parallelism. And this taking a spark out of the queue and evaluating it is called conversion. So sparks are created using the PAR combinator, but sparks can be dug, meaning that they're already a fully evaluated data constructor. Also, the spark pool can be full. Those are possible sort of failure modes of this thing. Sparks get converted, i.e. evaluated, but it could already have been evaluated. Your spark, by the time you get around to evaluating it, someone else could evaluate it already. And this is called fizzling. That is, it now points to a data constructor. Or it could have been GC in the meantime. So these are sort of possible failure modes in a sense. So here's some of our new graphs. So And the area of this graph is the total number of sparks that are being created. And we colour it green for ordinary being created, i.e. added into the spark pool, red for overflowing, and grey for duds. This next graph shows you the number of sparks converted per unit time, i.e. evaluated, run. And the area here is equal to the area of green here is equal to the area of green here. All the ones, well, most of the time, all the ones that get created eventually get converted. And down the bottom, this shows you the size of the spark pool for each core. So now we can actually see much more clearly why we're getting this terrible performance up here. What's happening is that all of our sparks overflowing right at the beginning, a few, this little green area here, a few get into the spark pool. The spark pool goes right up to its maximum size. It stays at its maximum size as all these other ones are overflowing, and then gradually we drain the spark pool. So that means we're only getting parallelism, you see, in this short period here. After the spark pool is empty, no more parallelism. It's all gone. So this is a sort of catastrophic loss of parallelism. We actually here are creating 100,000 sparks, but only a few thousand are being used in a sense. So I think this is great. You can actually see what's going on now. We also have a visualization that shows you how the granularity of the parallelism. Small sparks, big sparks. So this graph is dividing up the evaluation time of all your sparks into how long it took to evaluate. So at the far end, you've got sparks that took hundreds of milliseconds to evaluate. Down here, you've got like, a few microseconds to evaluate. And so the ones down here, this is terrible. The overheads of the spark evaluation mechanism totally swamp the benefits you're getting down here. So this can give you some indication of the granularity, and you can try changing your algorithm and seeing if this graph looks better. That can give you some feedback.
What is the size of the spark?
That's how long it takes to evaluate. So it's the amount of work, the granularity of your tasks.
So why is this bad? I think this is very good if you generate sparks which do a lot of work.
This is the total evaluation time of sparks between 2 and 5 milliseconds. So we have a lot of evaluation, but in very, very small sparks. So what you want is it to be sort of biased to that end, not biased to this end. This is showing you that we have a huge number of very tiny sparks. Whereas if it was all up here, it would show you that we have the same total amount of runtime, but in bigger sparks. Does that make sense? So we can diagnose some problems from this, just by looking at these things. You can see you've got too few sparks, not enough parallelism. The spark pool hits empty, or if your spark creation rate is very low. You can see if you've got too many sparks, you're overflowing your spark pool, which, as I showed you in that example, can cause a catastrophic loss of the parallelism. Over here, you can see if they're too small or too big. If they're too big, it's usually less of a problem being too small, but it can still be a problem if it means that you end up with not enough. It can cause load balancing problems between the cores. And there's some more subtle cases. I mentioned failure modes earlier about dud sparks and fizzle and GC. That gets reflected in the colours. And it's not usually a problem unless you see like, it's all orange or all grey, then there's something definitely going wrong. How much time have we got? 5 minutes, right, okay. So here's a demo then. So this is the program that caused the really bad, these terrible, let's see, -0. So there's the, we can show turn on the extra graphs. Scroll down, there's all the size of the section graphs. We can show the spark size. One of the nice features we've added is that you can select a range of time, and then the histogram shows you just for that period, which I quite like. And these things are all sort of infinitely zoomable, so I can zoom in over here just by scrolling and zooming out. Let's show you here. So what this program is doing is generating some work using Fib, generating 100,000 sparks and evaluating using the ParList combinator. ParList just makes all of them available So what I've done, what I've changed in the program is to make the size, the granularity much bigger. I've got fewer, bigger sparks. So that, yeah, the creation and conversion are now pretty good. And the runtime does actually improve. Yeah. Let me show you one real program, because these are obviously trivial benchmarks, just to sort of illustrate. So this is a program written by one of our partner teams. This is a black hole particle simulation divided into 3 phases. I don't know if you can see those red lines. Those are labels.
So these are not GHC black holes?
No, these are real black holes out there. This is national physics, Monte Carlo particle simulation. So this is using the trace event that you can add markers into the, because there's actually 3 phases to this program. It's running 3 different analyses on the same set of input data. So we divide it up into 3 sections. So that is quite nice for seeing what's going on. And again, you can see. So here we've got actually a small number of very big sparks. We've in fact only got something like 50 or so in total for the whole program now. And we're getting pretty good parallel speed up. You can see we're utilizing both cores very well. So that's that. I'm probably out of time, am I? Or 2 minutes? Gosh. In that case, I can tell you a little bit about the implementation. So what we've done is we've added, as I said, the event log is extensible, so we've added a bunch of new events. One is that we've added sampled events for spark counters. The RTS maintains a set of counters to say how many sparks have been created, converted, done, etc. And we just sample those counters every GC, in fact. And that's enough to do these graphs. These graphs is enough. Oh yeah, actually this is interesting. You can see that this representation doesn't really work very well when you've got a small number of sparks. This is creating one spark. So we might have to think about a better representation when you've got a small number of big sparks. Anyway, the point is the sampling the spark counters is enough to give you those ordinary graphs. But to do the histogram of how the granularity, how big those sparks are, we need this much more detailed node where we emit events for every single spark event. So every time a spark is created, converted, physical data, etc., then we emit an event. And this has a slightly higher overhead, but it means we can calculate this together. So there's some future work. We want to polish that histogram is not yet in the released version. There is a release that includes the other graphs I showed you. And there's some other extensions that we would like to do, which is sort of what I like to do this. We've got someone working on integrating the power events from the operating system. I think that would be very interesting. In particular, we also want to be able to generate events from Haskell code, so like the power monad library. What it's doing is not visible from the RTS, but if we instrument the library to emit events, then it's yeah, we'd like you to use it and tell us what's wrong. Is this helpful to you? Is there something else, some different way of presenting information that would be helpful? That's what we'd like from you.
I have one. The thing I find the biggest pain in the butt when diagnosing multi-threading issues in Haskell programs is contention, specifically lock contention, where you have a bunch of threads like banging against the lock.
You mean like N-bars?
N-bars and black holes on IRFs. Those are the 2 things that are the biggest.
Yeah, so we've only been looking at this pure parallelism, hard spark stuff, but you would want a different analysis to see. Because I think the events are either there or they would be easy enough to add for that sort of thing. Yeah, so you just need another visualization for that stuff.
Right.
For a 4KO concurrency model. Yeah. Other questions?
As I understand, it's just enough to use trace event and then these things get into the ThreadScope visualization?
At the moment, yes. I might change that because maybe people really want to use trace event for very high volume events. And maybe I should add a new one saying, trace marker to give, but it seems to be quite handy. So
for me, I use ThreadScope to define, and the most difficult part was to correlate the the phase of my program.
Right, exactly. So that, yeah, I think that's a nice example showing these delimited phases.
So it's great that the events system is extensible with new events. But what about extending existing events with sort of,
New fields.
oh, I was going to say, oh, I'm sorry, I'm blanking, hooks, like Emacs. So, for example, if I want to call a foreign function that makes a note of point and execution, it's an external library. I'm thinking of running it through binary translation-based performance analysis tools. It would be nice to mark the start and end events against an external library, something like hash mark.
So you want to see the transitions into foreign calls and back?
Oh no, I want to attach new foreign calls to GHC events. So when the spark is converted, I want to put a hook in that makes a foreign call and notes that point in time. Is there one? An alternative way to do it is if you could somehow reproduce.
In principle, you can do that. I mean, you make a new variation of the RTS that calls, this call, calls a stub function, and you DL to preload something, and it will call your thing. It's plausible.
So my bigger concern is that this is wonderful. This is like a quantum leap forward in looking into the mysterious world of R and Spark attacks. But I worry that unlike other parts of Haskell, this is a place where we really are missing the theory. In particular, SIL has some great theory where they can guarantee you won't have any sorts of problems like overflow or Spark. You have this bound where you multiply by process rules. And somehow Haskell's very high level, we somehow made this kind of programming extremely low level. We can't abstract it